This video is intended to introduce the concept of a cross product. Now, the significance of a cross product is given two vectors that are contained within a plane in 3 dimensions. Holy crap, yep, that's a plane allegedly. So, given two vectors within the plane, we'll call these u and v. The cross product of these two vectors is designed to be a vector that is orthogonal to both v as well as u. I realize that it's kind of difficult to envision this in 3 dimensions, but well, here we go. Here's v, and then here's a u, and then something orthogonal to both of them would be something pointing straight up. So orthogonal to both. So given a plane, this is how you wind up with something that's orthogonal to both of them. So this is referred to as the cross product. And it is defined in the following fashion. So the reason it's referred to as the cross product is similar to the dot product. We're going to use a symbol for multiplication that's sort of not really used once you get to a certain mathematical level. A little cross symbol that you have here. Now let's operate under the assumption that we have some components for these two vectors. We'll call them u1, u2, and u3. And then for the vector v, we'll use components v1, v2, and v3. Now the cross product is defined as the following vector. So this is a way that we multiply two vectors together and we wind up with a vector result. So this is going to be equal to u2v3 minus u3v2. That's the first component. Second component is going to be u3v1 minus u1v3. The third component is going to be u1v2 minus u2v1. Now, I have never memorized this formula, despite the fact that I seem to have just produced it out of nowhere. I was actually going through a little mental calculation in my head, taking a look at these things. Now, there is a slightly different way to represent what this cross product is, and I would like to introduce what this is. For those who have taken linear algebra, this is the determinant of a 3x3 matrix. For those who have not taken linear algebra, please allow me to explain what's going on. So to set up this determinant for this 3x3 matrix, what we're going to do is put our unit normal vectors, I, j, and k, across the top. Across the second row, in these 3 spots, we're going to put the vector u, or whatever is the first vector here. And across the third row, we're going to put the 3 components of the vector v in order. Now, normally I would say if this were a linear algebra class, do a cofactor expansion across the first row. But this isn't a linear algebra class, so I'm going to show you a little shortcut for what to do. What we're going to do is recopy the first 2 columns exactly as is. Now, I always like to use a little funny voice here because I think of what's about to happen as like the least intimidating horror movie character that you could ever think of. Because what I'm going to do here, I'm going to give you all a little slashy. I'm going to slash you up real good. Hope you don't mind. What I'm going to do is create a diagonal slash that goes through 3 elements. So 3 slashes in the down to the right, and then 3 slashes up to the right. What I'm going to do is I'm going to multiply everything on one of those slashes together. So on the bottom side of things, we have I times u2 times v3. So that's u2 v3 I. Plus the second slash that we get u3 v1 and j. So u3 v1 and j. And on the third slash, we get a u1 v2 and k. That'll be u1 v2 and k. Everything that we slashed in the downward direction, we're going to account for this with a plus sign. Now, similarly, slashing in the upward direction, we get u2 v1k, u2 v1k. For the next one, we have u3 v2 I. And for the last one, u1 v3 j. Everything that we slashed in the upward direction, we're going to account for that with a negative sign. What I'm going to do is match up everything that we just created in our little picture here, and we'll take a look. So for the I component, we have a positive u2v3 minus u3v2. That was u2v3 minus u3v2. For the j component, in the positive direction, we have u3v1, and in the negative direction, we have u1v3. So that was u3v1 minus u1v3 for the second component. For the third component, that would be the k's. That'll be plus u1v2 and minus u2v1. That was positive u1v2 minus u2v1. Now the significance of this vector is that allegedly this is u cross v is orthogonal to both u and orthogonal to v. Now the way that we show that things are orthogonal to each other is we take the dot product. Now rather than doing this with all of these hypothetical numbers and whatnot up here, I'd like to throw in some actual numbers. So in our next video, we'll take the cross product of two vectors and verify the orthogonality to both of the original vectors.